Hello, Algebra students, Mr. Lawrence here, and we're going to do a quick review of Mod 1 Lessons 1, 2, and 3. I gotta tell you, I've been really proud of you. Some of you have been working so hard. Kevin Merrick coming in for lunch, and Holly Krieger coming in after school, getting extra practice. Smart choices, ladies and gentlemen, smart choices. Some of you going home, I'm thinking like of Kyle Gray and Claire Ostrowski. Claire Madison Sorrell. I'm sorry, getting you mixed up in my mind. Going home and trying taking the ball and dropping it from a height of 10 feet so you can convince yourself that it is moving faster when it gets near the ground. You told me you're doing that. Claire doing a great job as secretary. Not trying to dish you there, Claire. Just getting you and Madison confused for a second. Anyway, keep up the good work. I can't believe how much you're learning in such a short time. I've been bragging to Mrs. Armitage. I'm just amazed at what you're coming up with. All right, so we're going to do a quick review here. Shouldn't be a very long video. Let's see. I've got 3 elevation versus time graphs here. And I need to know which one is linear. Let me see here. Let me put linear right here. Which one is quadratic? Okay, and I'm just stacking them so that they're not by any particular graph. You're going to tell me that. Exponential. Okay, and which one is exponential? And I guess it'd look really cool if I change the colors on these. Let's pick a real ugly color. Let's see here. Ooh, let's go to more. Oh, no, that's all black. I don't want to pick that. We won't be able to see it. All right, I guess I don't have any super ugly colors, but we can do that. All right. Come on now. There we go. And, okay. All right, well, they're a little prettier colors than I'm used to, but that's okay. All right, so I want to see if you can tell me which graph is linear, quadratic, or exponential. Hey, by the way, this would be a great time to pause the video, try to figure it out on your own, and when you're ready to see my answers, unpause the video. All right, here comes my explanation. Hopefully you've already paused and tried to match them up your own. Okay, well, linear means line, right? I've said that many times. Sometimes, I don't know why, some kids are thinking that linear means it has to go through the origin. No, absolutely not. Linear means line. It means it makes a line. So the only one that even kind of looks like a line is this. It looks like a whole bunch of lines put together. So I'll call this one the linear. And it's actually piecewise. It's a piecewise function, right? It's like a whole bunch of parts of lines or pieces of lines. See all the pieces of lines? Looks like there's 1, 2, 3, 4, 5, 6 different pieces of lines. This one might be used to explain like a person going upstairs and then going downstairs and then going back up a couple floors and then going back down to the ground. I mean, it could explain a lot of different things, but you know, if maybe they're on the 3rd floor and they go up to the 4th and then they go down all the way to ground level and then they go up to the 1st floor and then they go back down. Okay, so this would be piecewise function, but it's got a linear pattern to the data. All right, remember the quadratic is going to be used to explain things falling. Now, quadratics won't always open downward like this one is. Yeah, this is the quadratic. They can also open upward as well. Okay, and we can talk more about that at a future date. But for right now, we can think of quadratics explaining how things fall, and therefore they kind of have a downward trend to them. And remember that as it gets closer to the ground, it's covering a greater distance. And if you kind of piece it off here, if you look from this time interval here, see, it doesn't go down very much. But if I take that same time interval, let me see if I can, yeah, there we go. Oops. All right, hold on a second. I think they're together now. No, they're not. Okay. And I take that same exact interval and I put it, say, here. Well, you'll look, this one has to be extended. Best if I extend. Look at that. It's going all the way up there to all the way down here in that time interval, whereas this one's barely moving. It's barely going down any at all. All right, so that's a quadratic. That leaves exponential. Now, exponential is the one that really takes off. You know, at first there's only a couple, and then boom, in a short time, there's just tons and tons of whatever it is, okay? So if you could have your elevation change exponentially, that, you know, maybe it's a rocket going up. I don't know. I mean, sure, going up, it's going faster and faster and faster as it goes. I don't know if we have anything that really moves like that in the real world. I have to look into that. All right. I also expect you to be able to tell me if they're linear, quadratic, or exponential based on just the data. So let's see how we do that. Okay. Let's see, I get my words, and I'm going to bring them down here. Okay. Now let's take a look at this data and see if we can tell which one's linear, which one's quadratic, and exponential. Now linear, since it makes a line, it's going to have a constant rate of change. It's going to go up or down by the same amount. So check out these. This is going up 6 and then 18, and let's do plus 6, plus 18. Wow, what is that, 54? Okay, so that one's not going up by the same amount every time. This one here is going up 3, plus 5, plus 7. It's not going up by the same amount every time. Okay, but this one here is going down 3 more, down 3 more, down 3 more. It is changing by the same amount. This must be our linear pattern. Okay, this is a linear pattern. There's a constant rate of change. Now the quadratic pattern, you know, we'll do the exponential one next, and then we'll do the quadratic. The exponential one is actually pretty easy to identify if you know your multiplication facts. You see the plus 6 and the plus 3? That's the difference of times 3, isn't it? 6 times 3 is 18. If you multiply 18 times 3, you're going to get 54. Okay, now I didn't figure out the difference there, but I'll bet you it's 162. I'll bet you it is, because I know 54 times 3 is 162. When you see it doubling, tripling, quadrupling, quintupling, it's your exponential data. Yeah, because it takes off so quick. Look at the fifth time interval, fifth movement, we have 243. Way more than the other two columns. Now, of course, by default, that means that this middle one must be quadratic, but let me point out a pattern to you. Okay, now it went 3, 5, 7, 9. See how it's skipping 2 every time? If your pattern is skipping 2 every time, in other words, if the second difference is 2, then you've got a quadratic pattern. Okay, so there you go. All right, so here's what they look like. This was linear piecewise, this was exponential, and that was quadratic on the left. And then their tables, the linear patterns on the right, is changing by the same amount every time. It might be plus 6, plus 6, plus 6, plus 6. The quadratic is changing by 2 more each time. 3, 5, 7, 9, 11, etc. Could be 2, 4, 6, 8, 10, but it's always going to change by 2 on the first difference. Now, the exponential, the first differences are being multiplied by some number. Okay, they're being tripled or doubled, etc. So, linear, quadratic, exponential. All right, one more thing we need to go over here. You may be required to tell me a story here. All right, take a look at this. We've got this graph of elevation in feet versus the time in minutes. And I'm going to tell the story on this one, but you can make up your own if you like. I'm going to say that a person is launching a helicopter, and they're not very good at flying it, you know, like a radio-controlled helicopter. And that in a very short time, looks like it's about, let's see, 1, 2, 3, 4 blocks is a minute. That means each block must be 15 seconds, right? 15 seconds. So in 45 seconds, this helicopter has climbed to a height of, oh, let's see, that's 100. How many did I take to get there? 1, 2, 3, 4, 5. So each one must be 20. 100 divided by 5 is 20. So it gets to 120 feet. Okay, that's its elevation. Now the pilot is new, the person running the control, and so the helicopter dips 20 feet over the next 30 seconds. And then he overcompensates, and oh my gosh, he tries to get it to climb back up, but it climbs way high, way too steep. And it goes all the way up to 300 feet in the next, I think it's 30 more seconds, right? Yeah, I think so. Okay, so then the pilot starts to lose his altitude. And it looks like he drops from 300 down to 160 feet, right? 160 feet. I'm marking these so I don't have to go back and figure them out again. I guess I should call that 100. Over the course of how much time took place there? Let's see. 1, 2, 3, 4, 5, 6, 7. Looks like a minute 45 seconds. Looks like that's a minute 45 seconds. Then for a little while he gets it to fly, at the same altitude, which is kind of the goal. Looks like 15, 30, 40 for 45 seconds, and then all of a sudden, oh my gosh, he loses control, and this thing over the course of the next 15, 30, 45 seconds crashes into the ground, leaving him in tears. Okay, this is linear data, but I want to know if you can find the speed of the helicopter, the upward or downward speed, and we're going to find it of two segments. We're going to find it of that segment, and we're going to find it of this segment here. Okay, so let's see if we can do it. Let's do the yellow segment first. So we're going to do the yellow one first. Now, we know that this equation, d equals rt, right? And to find a speed or a rate, we have to get the r along. And so we're going to divide by t. And so then our rate is going to be the change in the elevation, or change in the distance, divided by the change in the time. Okay, so let's see here. How much did it climb? It looks like it climbed from 0 to 120 feet. I'm going to write 120 feet. Over how much time? Now, it looks like 45 seconds. Now, I could put a 45 under there and then divide or simplify. But since the elevation is in feet and the time is in minutes, I'm not going to put 45 seconds there. That will get me the feet per second. I'm going to do it as 45 seconds is 3/4 of a minute. 3/4 of a minute, right? Now, why am I doing this? Because remember, I've told you sometimes it's smarter to use a fraction than it is to use a decimal. Watch how easy it is in this case. I'm going to rewrite this 120 over 1 times, and remember, I have to use the reciprocal of 3/4, 4/3. And now I get to look for Wonder Woman. And here she comes. 3 goes into 120 40 times. 4 times 4 is 16, so 4 times 40 is 160 feet per minute. So in other words, this helicopter was climbing at a rate of 160 feet per minute. Okay, so it's not super duper fast, but then again, the person is only amateur learning how to do this, so pretty cool nonetheless. All right, let me get a little more space here, and now I'll do that blue one. And you would say that was a positive 160 feet per minute because it's climbing upward. All right, where's my highlighter? There it is. Okay, so now we're going to do the blue one. And the cool thing is we get to use the same equation. We don't have to go back and rederive it. We know the rate is going to be the change in the elevation divided by the change in the time. And so my change in elevation looks like I'm going from 300 down to 160. So let's see, it's going to go, right? Is that down to 160? Yeah, I think it might. No, yeah, that's good. Yeah, it's a change of 140 feet. It's confusing myself a minute. And if you want to make it negative to indicate direction, that's quite all right. Go ahead and make it negative to indicate the direction. Now the time, looks like it's going from here to here. It's like 1, 2, 3, 4. There's 1 minute, and then 15, 30, 45. So 1 minute, 45 seconds. Well, that'd be like 1 3/4. Now I don't want to use 1 3/4. I personally think it's harder to use that. So I'm going to use improper fraction. And I'm going to go 4 times 1 plus 3 is 7. And I'm dividing by 4. So my fraction is 140 feet per 7/4 minutes. Now I'm going to do the 140 over 1 times 4 over 7. Remember, to divide by a fraction is the same as to multiply by the reciprocal. And then Wonder Woman shows up. And 7 goes into 7 once, goes into 140 20 times. 20 times 40 is 80. I'm going to call it a negative 80 because it was going downward. So it's descending at a rate of 80. And then again, I'm in feet per minute. Okay, feet per minute. Now, if I'm going to say descending, I probably won't put the negative there. If I'm going to say it's changing by negative 80 feet per minute, I'm telling the reader it's going down and it's going down fast. Now, does that make sense? You look at the yellow highlighted segment. It's going up 1, 2, 3, 4, 5, 6 blocks for every 1, 2, 3 it goes over. So it's like 6 over 3 or 2 over 1. But this one's going down 1, 2, 3, 4, 5, 6, 7 and going over 1, 2, 3, 4, 5, 6, 7. It's going down 7 over 7, or better yet, like that, simplified, right? So this is going twice as fast. It's climbing up twice as fast, isn't it? Now look, isn't 80 times 2 160? So the red one is twice as fast. So you see, it makes sense on so many different levels. Sorry, a little keyboard action popping up there. All right, I think that's it for the video tonight. We're going to be having a quiz later this week. Mr. Lawrence signing off. Have a good night, everybody.